Welcome back. Now that we've talked a little bit about asynchronous programming versus parallel programming, task, thread, it's time to dive a little deeper. To really understand how async works in C# in .NET, we actually need to look at the compiler-generated code. But before we jump into the code, let's walk through a simple example, and then we'll look at how the compiler takes our code and generates a lot more code under the hood. Here, we have a method called getLibraries. It's an async task method that returns a type of task of list of library models. Let's walk through this code together to really understand what's going on with multi-threading under the hood. First, let's assume thread 1 calls the getLibraries method. So thread 1 is going to enter the method and initialize our variable response. But then thread 1 hits this await keyword, and immediately thread 1 returns, while thread 2, a background thread, runs getAsync. Now, getAsync could be running on any available background thread. For this example, we'll just say it's running on thread 2. But anytime a background thread is needed, .NET fetches one from the thread pool, and it just picks whichever one is available. So this could be running on thread 7, it could be running on thread 6, but for this example, we'll say it's running on thread 2. Now, this is very, very important that it's not running on thread 1. When thread 1 hit the await keyword, thread 1 returned, and thread 1 is now available to interact with the user. And this is really, really important because thread 1 is also known as the main thread, and it's also known as the UI thread because thread 1 in any application that has a UI is the only thread that can draw that UI. Thread 1 is also the only thread that can respond to user input. So if a user is scrolling through our app or tapping on buttons, it's thread 1 that responds to those button taps that redraws the UI as the user scrolls down the screen. And in this scenario, let's assume getAsync takes 15 seconds. Well, running on thread 2, that's not a problem. Thread 2 is a background thread. So while getAsync is running, we can show a little activity indicator to the user, letting them know that we're doing stuff in the background. Meanwhile, the user can choose to navigate away from that page. They can choose to scroll. They can continue interacting with our app. Our app is not locked up. Our app is not frozen because getAsync is running on a background thread. Now, if we were not using async await and we called getAsync from thread 1, well, thread 1 would be locked up here. Thread 1 would be busy for 15 seconds downloading all this data from this Get API. And during those 15 seconds, thread 1 would not be able to respond to any user interaction. So if thread 1 was calling getAsync, for 15 seconds, the user would try to scroll, they would try to tap, and nothing would happen. For all intents and purposes, our app would be frozen. The user then does what? They force quit our app, they give us a 1-star review in the App Store, they tell all their friends not to download it, and it's a bad day for us. But fortunately, with async await, as long as we use the await keyword, that allows the calling thread, in this case, thread 1, the UI thread, the main thread, to return while getAsync runs on a background thread. So once thread 2 is done, once getAsync completes, it calls back to thread 1 and says, hey, I'm all done, get back in here. And what happens is thread 1 jumps back in to run these next lines of code. So thread 1 runs response.ensure status code, and then thread 1 also initializes this variable stream. And then again, we hit the await keyword where thread 1 returns, and now response.content.readAstream.async is running on a background thread, in this case, thread 6. Once readAstream.async is finished, it calls back out to thread 1. Thread 1 returns to the method, initializes our variable libraries. We hit the await keyword again. And now deserialize async is running on a background thread, in this case, thread 5. When deserialize async has finished, just like last time, it calls back to the calling thread, thread 1, and says, hey, thread 1, I'm all done, get back in here. And thread 1 jumps back in to return the result, return libraries, or throw an exception if it's null. Now, this is a bit of a simplified explanation, and I am making a couple assumptions along the way to help keep things simple. Again, we're going to dig into the compiler-generated code, but before we jump in, let's talk about those assumptions just to make sure we're all on the same page. The first assumption here is that we are always doing work on a background thread anytime we call the await keyword. In reality, if this task, if get async has already completed, or if read-to-stream async has already completed, or deserialize async has already completed, then .NET doesn't actually jump to a background thread. It'll continue on using the calling thread, in this case, thread 1, would just get the result from the get async task. However, in this example, it's safe to assume that get async has not completed yet because we're calling it directly from HTTP client. Likewise, with read-to-stream async and deserialize async, if those tasks had already completed, then we'll just get those results from the task instead of switching threads. .NET's smart enough to detect that and smart enough to avoid switching threads because every time we switch threads, we do take a performance hit. It does cost some CPU cycles to switch back and forth. And if we can avoid that, we should. And the good news is .NET avoids that for us. The other assumption here is that I'm in a .NET MAUI app. Now, if we're in an app that has a UI like .NET MAUI, like WPF, like WinForms, like UWP, we have a main thread. Therefore, we don't want to lock up that main thread because it's also our UI thread. However, there's other .NET apps that we can make without a UI where this doesn't necessarily apply, but we'll dive deeper into all of that in this section and later on in the .NET internal section later on in this course. So let's jump into the compiler-generated code to see what's really going on under the hood.